Next, we need to discuss a more technical concept called normalization. Let's say that the system is in an arbitrary state theta. If I multiply this state by an arbitrary complex number a, I get a times theta. You can easily convince yourself that for these two states, the probabilities p0 and p pi will be exactly the same. And so there is a third postulate of quantum mechanics, which says that as long as a is not equal to 0, these two represent exactly the same state. That means you can take any state, multiply it by any constant except for 0, and you'll end up with a formula representing exactly the same state. So we can use this to normalize states. For example, if we take a look at this state again, this represents exactly the same state as I over square root of 5, 0, minus 2 square root of 5 pi. I have just multiplied by 1 over square root of 5. In the second formula, I have what's called a normalized state. So the requirement for a state to be normalized is that phi 0 square plus phi pi square should be equal to 1. You can check that the right-hand state actually is normalized. I square root of 5 square plus minus 2 square root of 5 square is equal to 1 over 5 plus 4 over 5, which is indeed 1. So we tend to prefer to work with normalized states. And one of the reasons is that the formula for the probabilities will become much simpler. If the state is normalized, then p0 will simply be equal to phi 0 square, while p pi will be phi pi square, as the denominator cancels since it's equal to 1. Extending this model to a case where I have m holes and therefore m pure states is straightforward. For example, if m is equal to 4, the pure states will be 0, pi half, pi, 3 pi half. Those will be the pure states. An arbitrary state, theta, will then be a linear combination of these four pure states. So we can write that as phi 0, a complex number, times 0, plus phi pi half, plus phi pi, plus phi 3p half, 3 pi half. We say that this state is normalized if the sum of squares of all these coefficients is equal to 1. If the state is normalized, then the probabilities are simply given by p0, probability of finding it in the right hole is then phi 0 square. P pi half, the probability of finding it in the top hole will be phi pi half square, and so on. We see that the system is completely represented by m complex numbers. In the classical mechanics system, we could represent the position with just one angle, a number between 2 and pi. In the corresponding quantum mechanics systems, we need m complex numbers to represent the system. On the other hand, those m complex numbers will represent everything there is to know about the system. There will be no additional information in the system in addition to these m complex numbers. Further, the length of each of these complex numbers will give us the probability distribution function, probability that we will find the electron in a given hole. So in the next lecture, we'll move on to a continuous system by letting m go to infinity. Instead of having m complex numbers representing the state of the system, we'll have an infinite number of complex numbers. That is, we will have a complex number everywhere on the x-axis, and the amplitude of these complex numbers will be replaced with a function like this. A function that's commonly called the wave function in quantum mechanics. So we'll see that then we go from a discrete random variable to a continuous random variable, but we will still be able to find probabilities of finding the particle in a certain position. It's just that now we need to integrate over intervals to find these probabilities. And then we'll move on and expand space and make it three-dimensional. We'll also introduce dynamics into the model. So at a given point in time, the system is in a certain state represented by these complex numbers, and in a later point in time, it will be in a different state with different complex numbers. And we'll look at the dynamics that tells us how this state changes over time. And that will take us to the famous Schrödinger equation.